Okay, this will be the Chapter 8 review, the conic sections for pre-calculus. We'll talk about parabola, circle, ellipse, hyperbola, and go through some of the completing the square examples and all that good stuff. So let's take a look. The first type of problems you'll probably see are something like this, where they just kind of give you an equation that looks just like a big long string of variables and x's and y's and y squareds and all that stuff, and we need to figure out what it is. Okay, so what I would suggest doing in problems like this, anytime like this, kind of look at your variables separately. Like think about your x's as one group and your y's as another group. And in this case, since I'm seeing both of them have a squared term in there, again, I know it's not going to be a parabola. So in any other case, you want the x's and y's to all be on the same side of the equation, and you're going to want to just get whatever the number is, the constant on the other side. So let's move that 76 over by subtracting it, so minus 76 on both sides. And let's go ahead and arrange these x's here. So we have 9x squared minus 54x, and then we have the y squared plus 4y. And I left a little space because, again, I want to complete the square. Because if you think about any of the formulas for an ellipse or a hyperbola or a circle, all of them have something like some sort of x minus h squared and y minus k squared, like somewhere in there. So what we want to do is I basically want to turn this guy eventually into this. And then eventually I will want to turn this guy into this. Okay, so in this first one, I'm going to go through a little bit more in depth on the completing the square, and then we'll go a little more quickly through the other ones. But any conic section, basically, you're going to want to do completing the square. It's just the way all the formulas work. So with this one, with the x terms, they have a coefficient on there, that 9 on there. You want to bring that out front first. It's much easier to complete the square if you just have an x squared. Don't forget to divide this one by the 9 also, so that's going to become minus 6x. And then we're going to complete the square. We'll talk about that in just a second here. We'll do a similar thing with the y values. Okay, that one actually didn't have a coefficient, so we don't need to worry about bringing anything out. But we will complete the square there. And it still all equals a negative 76. Okay, so figuring out what number goes in the space there. Okay, again, I eventually want this to be able to be written in a couple steps as 9 times something with an x in it squared. And we're trying to figure out, what number would go here in the C position to turn the whole, this whole thing into something that's a perfect square. And that's what we're going to try and figure out, what would just make it work nicely. So let me do a little separate side page real brief, and again, this is just to show why completing the square works. I think this might help. A little bit of algebra background stuff real quick. So if you consider two different things, like let's say we consider this, okay, versus this. Okay, and we'll come back and finish the problem in just a sec. But basically, the completing the square, what happens is if you think about just regular old factoring, okay, the way it works is normally you need two numbers that multiply to be the C value that add up to be the B value. Okay, so in this case, those numbers would be 4 and 2. So this would factor into x plus 4 times x plus 2. Okay, and you should be able to check that out if you were to distribute it out, FOIL it back. So I'm just kind of foiling out here, just verifying that it's factored correctly. Do your x times x, x times 2. And see how these two add up to give you the 6x in the middle. And then the 8, of course, is the 8 on the end. So that would factor into just x plus 4 times x plus 2. Okay, so this would be the factored form of what we started with. The one on the right doing a similar deal here. If we need two numbers that multiply to be 9 but add up to be 6, in that case it's going to be 3 and 3, right? So x plus 3 times x plus 3. Okay, and again, you can check that by foiling it if you want to. X squared plus 3x plus 3x plus 9. So that just kind of verifies, there's your 6x in the middle. But the way we usually write something, or the way we can write it, if it's the same factor twice, x plus 3 times x plus 3, I can just write it as x plus 3 squared. And this is the version of things that are in these conic sections. It's always x minus h and it's all squared, or y minus k and it's all squared. So what we're doing on the other page is basically saying, what if we don't know this c value? What if that's unknown? how do we figure out what to put there? Okay, so what I want you guys to recognize is that whatever this b value is, when you cut that number in half, so 6 cut in half is going to give you the 3 and the 3, so the 3 times the 3 is what needs to go right here. So that's why it has to be a 9 there. If it's an 8 there, we don't end up getting a nice perfect square trinomial. We got two factors that were different from each other. Okay, so going back to our problem, in this case, um, in the highlighted green there, x squared minus 6x, what does the c need to be? So the process is, look at your b value, take half of it, so that's -3, and when you square that, you end up getting a 9. Okay, down here it would end up being, just to show this step, the factors are x minus 3 times x minus 3. Okay, so it's x minus 3 all squared. Okay, with the y's, okay, same thing. I'm going to be looking at, based on this value being a 4, half of that I know is 2, right? So y plus 2 times y plus 2. So that's y plus 2 squared. So the c value here would need to be 2 times 2, which is also plus 4. Okay, and then we still have this plus sign in the middle here. Okay, so now we completed the square, the things we added. Okay, when I say complete the square, I'm basically saying find the correct c value that makes it work. Okay, so there's the c value there and there. Now what we need to do, since we added something to the left side of the equation, we need to add them to the right side as well. We need to balance out what we did. Okay, so here's where it gets a little tricky too sometimes. It looks like we just added 9 right here, but that 9 was really getting multiplied by a 9 out here. So it's really like we added 81. Okay, so on the other side of the equation, I need to do the same thing to keep the equations equal to each other. Okay, 9 times the 9. Over here, we just added 4. There was no multiple out here to multiply that by, so balancing out, just add 4. Okay, and if we just combine those things, you can check my math here, but these should add up to just become a 9. Okay, so there's our equation with the squares completed at least. Now, here's where you kind of need to know the forms of things. Basically, if this front 9 was not there, we would have ourselves a circle, like x minus h squared, y minus k squared equals r squared. Okay, but we had a 9 there. So what we need to do, whenever that happens, you need to divide out. Okay, so what I'm actually going to do is I recognize this thing is going to become an ellipse because we're going to have denominators once we divide. But I'm going to divide every single term by 9. Okay, and that will make the right side of our equation a 1, which is what we need. Anytime we do an ellipse or a hyperbola, it always needs to equal 1. And that's exactly what we have over here. Okay, so on the other side now, the 9 over 9 on the far left will cancel out. Okay, and it actually just becomes a 1. In the middle term here, it was like 1 over 9, so we don't really need to write the 1 in the numerator. So we just have a 9 in the denominator. And now we are able to graph this thing. Okay, so here's what I'm thinking. It's going to be an ellipse. If you're graphing by hand real quick, I'll show you the hand and then I'll show you on the calculator version. But basically just the basic setup by hand is a circle with center. Oops, I don't want a crayon. Let's do the highlighter. Our center is always going to be what's in the numerators, right? So with the x in parentheses is -3. So I know it's going to be over at +3. And the y is a +2, so it's going to be down 2. Okay, parentheses are always go opposite direction. There's my center. Okay, this 1 being under the x tells me my horizontal stretch is going to be 1 in each direction. So I'm going to go out 1 and 1. Okay, and this being under the y is telling me vertically I'm going 3. Okay, those denominators are already squared, so that actually is a squared. And that one is b squared. The bigger one's always a for an ellipse. So I'm going to go up and down 3. So from the center, 1, 2, 3, and down 1, 2, 3. And my ellipse will go something like this. Okay. So let's jot down what we have. A squared is 9. The bigger one, that's your major axis. B squared is 1. The smaller one is your minor axis. We're going to have some foci. Okay, let me draw the axes through here. Okay, remember with an ellipse, they have two focal points. They're going to be somewhere inside, somewhere in there on the major axis. To figure out where they are, okay, we have to find the distance from the center, which is c. So when I graphed them, I just kind of estimated for now, so I wouldn't plot those yet, but I just wanted to visualize it. But we need to find c. Okay, so c, which is the distance to the focus, distance to both foci. And the formula in this case, if you think about how an ellipse works, A is the biggest one. Okay, the foci, which are c units away, is smaller than A. Okay, so let's visualize that. So A is from here to here, while C is only from here to say there maybe. Okay, so A is the bigger one. So the formula, the Pythagorean-like formula, is going to be that A squared, being the biggest one, is equal to the other two squared added together. Okay, so A squared is 9, B squared is 1, we don't know C squared. We're going to subtract the 1 from both sides and get 8 equals C squared, so the square root of 8 equals C. And if I remember correctly, that number's around 2.8. Let me just check real quick on a calculator. The square root of 8, I know it's a little less than 3. Yeah, about 2.8 roughly. Okay, so that's the distance from the center for our foci. So let's list everything kind of clearly here. Center from the beginning was at 3, -2. Okay, we had vertices. So we can color code this a little bit. Vertices here and here, the ones on the major axis, it looks like we added 3 to the y value and subtracted 3 to the y value. Right, so it should be at 3, 1, and 3, -5. Okay, we had co-vertices over here if you need those, depending on what the question's asking about. So those are from the center, adding 1 and subtracting 1 from the x value. So from that value, so 2, -2, and 4, -2. And then we just found the foci as well. Okay, foci. Okay, on the major axis. So in the y direction, we're adding and subtracting root 8. So it was 3, and then add root 8 to the y value up from the center, and 3, -2 minus root 8. Okay, and that'd be a nice exact value. Okay, so a lot of stuff there. All right. Number 2. Oops, that's the other example that we did. Okay, let's do the completing the square here, because this one's a touch different. This one's the parabola, and I know that because there's only one squared variable. Okay, this is the only one with one squared variable. Okay, so just the x's are squared. So let's arrange things. We have 3x squared plus 6x minus 2. In this case, I'm going to get the y on the other side. Okay. And again, I'm thinking, if you think of like a basic quadratic equations, y equals a x minus h squared plus k. Sorry, I ran out of space. But it's just one variable squared. Okay, and in the way I just wrote it, just the x side is getting squared, and the y is like totally by itself on the other side. Okay, so we might want to take care of that issue, because right now I have negative y. So if you want to divide everything by -1 and get that to be a positive y, that's an option. Otherwise, from the beginning, you could have subtracted this, this, and this to the right side and left the y alone where it was. So that's up to you, but that's just kind of intro algebra, whatever you want to do there. But this isn't too bad. So let's divide them all. So that's going to become -3x squared minus 6x plus 2 equals y. Okay, and then if we want to do this completing the square method, we're going to do a similar process. I'm going to, looking at these two, divide out the -3. Okay, so x squared. Careful here, this is actually going to be plus 2x. If you check and distribute the -3 times the positive 2, you'll get the minus 6x that we had up here. We'll complete the square. Leave that plus 2 alone on the outside. That's not a perfect square. That's not the c value we want. Okay. So now I can go ahead and do the process where I'm going to take half of my b value, so that's going to become 1. 1 squared is still 1. So this is going to be negative 3. Okay, think about the quadratic that we just created here. Okay, this right here is a perfect square trinomial. It's x minus 1, I'm sorry, x plus 1 times x plus 1. Okay, right, and 1 is 2 in the middle. 1 times 1 is 1. So there's that. We had this plus 2 sitting out here. We need to balance out what we just did. Okay, we added a 1 right here, but the 1 was really getting multiplied by a negative 3, so we really added a negative 3. Okay, so this time you have two options. You can either throw the negative 3 over here to balance it like we did on the previous problem. Okay, or which might be better in this case, because remember I want that to just be y still. Instead of putting a minus 3 on the right side, I can put a plus 3 on the left side. Okay, and then those two would just combine to be a plus 5. So the plus 2 and the plus 3, we might as well combine those. And that's going to be your vertex form now. We can see what the vertex is. Okay, the vertex is the h and k, like usual. So there's your x coordinate. So that one goes opposite. This one is regular because it's not in parentheses. There's our vertex. So let's take a look at this graph. Okay, this one I used the Desmos. First off, there was the one from number 1, a little bit nicer drawn. Remember, we plotted the center and whatnot. Okay, this one's going to look like that. Okay, we just found our vertex was at negative 1, 5, so you can see it here. Now, if we need focus and directrix and all that stuff, let's go back to what our equation was real quick. So our equation, a value was negative 3, right? So that's my a value. So that's going to help me get the directrix and focus. Okay, so let me just jot this down. A was negative 3. And the reason I want to know that is because, again, from the vertex, there's going to be a focus in here somewhere. I just don't know where. But I know that little distance from there to there is what we call P. And I know that P is 1 over 4A. Okay, so to find the focus, and directrix will actually be the same thing, but it's just going to be a little bit above. So if we want to find P, and we know A, I know A is negative 3. Okay, so P is actually 1 over negative 12, or negative 1/12. So 1/12 away from the vertex. So it's actually, I drew it like kind of far away. It's going to be real close, right? I mean, 1/12 of a unit, it's going to be, I mean, basically like right there. So what are the coordinates there? There's going to be a focus right there. So the focus, the x value is still negative 1. The y value is 1/12 less than 5. Okay, or if you want to be a little neater on that, 5 minus 1/12 is going to be 4 and 11/12. Okay, so that's going to be the focal point. And the directrix, again, will be 1/12 of a unit above the vertex. So the directrix, which is this line right here, it's a nice horizontal line. The coordinates are the equation y equals 5 and 1/12. Okay, 5 plus 1/12. There it is. Okay, 3 and 4 I kind of had already worked through, so let me just kind of walk through some of the steps real quick. First off, again, I'm going to think about getting my x's and y's in order, kind of like we did with number 1, get the 29 to the other side. So some of this stuff on the right there we haven't done yet, but we'll get to it. Very similarly to number 1, I'm going to factor out those leading coefficients. Get a little highlighter here. So basically this 4 got brought out here. This 9 got brought out here. Notice this one had a minus in the middle. It's going to be a hyperbola. And then again, we complete the square. So this was what we had to add. It came from the b value being 4. I did half of 4 was 2, square it. Okay, same thing here. I did half of its b value, so half of 2 is 1, and square it. Okay, so hopefully we can see now where the 16 came from. This came from when I added 4 in the x term. because again, that 4 was actually getting multiplied. I'm talking about this 4 was getting times by 4. So that's why this is a 16 being added. And likewise, that 1 was actually getting multiplied by a -9. So that's why I had to balance it with a -9 there. Okay, then each thing can be factored because they're both perfect squares now. We can get to our closer to our vertex form. Okay, so again, this one equaling 36, so you always want to divide that out because again, we had coefficients out front, so I can't just leave those there. I have to divide out the 36. So dividing every term by 36 got me this guy right here. Okay. All right, and let's look at the graph of that. It's going to be an ellipse, or I'm sorry, a hyperbola, right? This is the one with the subtraction. So you can notice from the very beginning, there was a minus. The 4x squared was positive, but the minus 9y squared. So whenever they're different signs, you're going to get your hyperbola. Okay, so let me pull the graph up on Desmos here, and we'll talk about some of the details. So there's that one. Okay, so basically, you can kind of tell that the center would have been, if we go back to our picture here, the center is going to be at -2, -1. Okay, so -2 and -1, there's the center. And it looks like we went out 3 in the x direction, and I believe it was 2 in the y direction to get the rectangle. Okay, those came from the denominators, right? The 3 was, or the 9 being under the x term, right? So that's why I went out 3 in the left and right direction, 3 each way. This, I'm sorry, up and down we went 2 each way, and that kind of gives you the width of the graph. Okay. Then since the x term came first in the order we wrote this in, if you remember, this is a subtraction problem, so the order is definitely important. That's why the branches go out to the sides and not on the top and bottom. Okay, so if we needed some information here, there's a vertex, there's a vertex. So my vertices for this problem, again, if this was -2, -1, and we added 3 and subtracted 3 from the x value, right? So the vertices were 1, -1, and -5, -1. Okay, this one doesn't really have covertices. Okay, there's no other points on the graph up there, so no covertices. But what this one will ask you about is transverse axis and conjugate axis. And of course, we'll do the foci in a second here. Okay, in this case, the transverse axis is basically asking for the length of this axis. It's kind of like the major axis in an ellipse, but it's not necessarily always going to be the longest one. So if you remember in this one, the order it's written in tells you which one's the transverse. So the x squared came first, so that along the x is the transverse axis. The conjugate axis will be the one vertically through the center. We'll do that in a second. But what they're really asking here is what is the length of it? Okay, so since from the center we went 3 to the left and 3 to the right, the total length of that is 6 units. Okay, in the y direction we went up and down 2. So the conjugate, that's the other axis, was 4 units long. Okay, and then the last thing we need here was foci. So the foci in this case, they're actually going to be somewhere outside of the hyperbola, kind of inside the parabola branches itself. So in this case, it's the c value that's larger than both the other values. Okay, so in this case, the equation is going to be c squared equals a squared plus b squared. Okay, with the ellipse, we started with a squared because the a was bigger. Okay, so in this case, it's a little different. So let's find those, or let's find that, I should say. So c squared, a squared was 9, b squared was 4. Okay, let me just make sure we had those right. Those are the denominators. Yep, 9 and 4, right? Okay, so c squared is going to equal 13. So c ends up being the square root of 13, which should be somewhere between 3 and 4. Okay, so they're actually going to be a little bit closer here. If we go from our center and we count out, let's just get a better idea. Is it closer? Square root of 13, 3.6. All right, so if we go out about 3.6, so maybe about there, 3.6. And coordinates there would end up being one of the foci, the x value. We're basically taking our -2 and we're adding the square root of 13. And the y value is still -1. Right, and then this one out here, we are taking our x value and we are subtracting the square root of 13. And the y value is the same. Okay, so that's everything for the hyperbola. Okay, I kind of just tried to draw it out by hand, so that's showing the same thing. All right, lastly, number 4, again, let's get the screen shade so we don't get overload here. Same kind of deal, I'm bringing 15 over, x squared and y squared, so I want to complete the square on both of them. Okay, so I'm kind of getting them in order. I just rearranged some terms, get the x's first, then the y's, complete the square like we did before. And you can kind of verify your work here. X plus 3 all squared plus y minus 1 all squared. Okay, notice that we balanced everything out nicely. Right, I added 9 here, so I'm adding 9 to balance that. I'm adding 1 to the y, so I'm adding 1 to balance that. So the right side ends up being a 25. And this one we can actually leave just like this. There are no coefficients. You'll notice out here it's just like a 1 and a 1 basically. So I don't have to divide anything out as long as those are both 1s. We're good to go. This is just going to be a circle. If you did, okay, let's just say you notice you had that 25 there. If you divided everything by 25, that'd be okay. You would just end up with, you'd have 25s down here on both if you wanted to do it this way. And this thing would be the 1. And you could kind of plot it just like an ellipse, and it would go out 5 in the left and right and 5 up and down. So it's going to be like nice and circular anyway. So that's why we don't need to do that. If you just recognize that this is actually just a circle with radius 5, you can save yourself that step. Okay, so on that one, just to kind of show it nicely on the graph here, it's just a circle centered. Where was our center? Centered at -3, 1. Okay, that's going to get you the center of the circle, h and k, opposites. So -3, 1 is the center, radius is 5. So we should be able to see that, you know, -3, 1, and it's just basically 5 units all the way around the circle. Okay, so if you're drawing it by hand, that's what I usually do. Just go up, down, left, right, get 4 other points, and then just make your circle. Okay, I think that's all we need for that, center and radius. Okay, the last few, if we need a circle entirely in the 4th quadrant, I'm just going to give you like a sample answer here. What you need to do is just make sure that your center is somewhere down here, and just make sure that the radius isn't too big to get out of the 4th quadrant. So a sample answer might be if your center, let's say your center is at like -5, -2 or something. So you would need to make sure that it's x plus something, and y plus something. That's going to make sure that the center is actually both negative coordinates here, and then just give it like a small radius like 1 or something, or anything small enough to keep it in the 4th quadrant if would work. Okay, so that's one possible answer. A hyperbola with vertical transverse axis centered at the origin. So again, I'm thinking something like this. Vertical transverse means that I need my branches to go this way. I need to be centered at the origin. So the numerators can't have subtracting anything in them. Now with this one being a hyperbola, it's a subtraction, and if we have a vertical transverse axis, the y squared has to come first. And then we could basically make these denominators anything we want. It really doesn't matter. So that could be anything and anything, okay? The order is important there, equaling 1's important. An ellipse with a center in the 3rd quadrant. Okay, so if we're centered, oops, I'm realizing I think I just did a previous problem wrong in the 4th quadrant. Uh-oh, glad I caught that. We need to be over here. This is a 4th quadrant. So the coordinates would actually need to be like a positive x value and a negative y value. All right, so this was wrong. So that's going to make this sign with the x needs to be a minus something. Glad I caught that. Okay, so that one's the minus, that one's a plus to get you down in the fourth quadrant. So sorry about that. We didn't get too far past that. Third quadrant, though, was with an ellipse. So let's use our coordinates for that one. Let's say we were at like, -5, -2 or something. X and Y both negative down there in the third, right? Horizontal major axis. So that means that when we write our form, okay, we'll do x plus 5 squared over something. We'll think about that in a second. Y plus 2 squared over something. In order to make the horizontal be the major axis, that means that this number needs to be bigger than this number. Okay. Otherwise, this thing would have a vertical major axis if it's under the y. So you pick two numbers, make the one under the x be bigger. All right, and finally, parabola with vertex, -2, 1. Okay, so if we're over at -2, 1, and we need to open to the right. Okay, so these get a little tricky when they open right or left. Okay, so I know it's going to be x equals something because it's opening sideways. Okay, I know the a value needs to be a positive number. Any positive number gets you opening to the right. So you guys can pick the a value. Okay, now it's going to be y. Okay, think about y coordinate of the vertex is 1. But we're dealing with the in the parentheses part, so it's opposite. And the x part of the vertex is not in parentheses, so it's just whatever it really is. So something like that would be useful. Again, that one's kind of weird to think about that way, but as long as your a is any positive number, you're good to go. Okay. All right, and then lastly, the definitions. Just I'll do these real brief. The circle, what you need to show me is that basically, if you have a center there, any point on the circle that has some distance, if you were to go to any other point anywhere, that distance would be the same. Okay, and show me at least 2 points. For a parabola, the geometric definition says that basically you have a parabola, you have a focus, you have a directrix line, and any 2 points. Okay, let's do one at a time. If you took any point on the parabola, and my drawing's not super accurate, I guess, but that distance and this direct distance, so my drawings are really bad, but those distances would need to be the same. Okay, if I were to take any other point on the parabola, there's some other distance, and those 2 purple ones would need to be the same. Okay, not the same as the blue, but the 2 purple are the same as each other, the 2 blue are the same as each other. Again, my drawing's bad. But that kind of shows the definition, right? We're always the same distance from the focal point to the directrix. Okay. And if you happen to do it from the vertex, that distance that you get happens to be p in both cases. So that's just a little side note. Okay, with the ellipse, okay, you have 2 fixed points in the center somewhere. And the way these work is if you take a point on the parabola anywhere and you get a distance to each, let's say that's d1, d2, okay, the sum of those distances would be the same anywhere on the parabola. So for instance, if I have a point here and I call that d3 and d4, okay, we're going to have the exact same sum all the way around the ellipse. Okay, so that shows the geometric definition. And then hyperbola is a little similar to that. Let's say we have a hyperbola like this and like this, and we have foci here and here. Okay, if we were to take a point, any point on the hyperbola, and go to the one foci to the other foci, focus, and those are some distances. And let's say I took some other point. It could be on up here or down here, anywhere on the parabola, hyperbola. I keep saying that wrong. And we find those distances again. What happens here is the difference in those distances remains fixed. So for example, D2 minus D1 would have to be the same as D4 minus D3. Okay, so that would be your definition for the um, hyperbola. Okay, and I think that covers it. Yep, kind of a long video, so sorry, a lot of stuff to fit in there. My advice again would just be try not to really memorize all definitions. I mean, you kind of need to know these geometric ones a little bit, but as far as all the other formulas with H and K's and A's and B's and all that stuff, really try to just look through the shape and think about once you get something, think about how they're all similar. Like you're always going to find your center or your vertex by this kind of stuff. Okay, if there are denominators, that's how far you're going to stretch. If there's not a denominator, this is going to be your radius, that kind of stuff. It really gets hard to memorize everything. Um, so hopefully just by working gradually, they'll work out. Again, sorry about the length of the video.